If we are given a curve such as this, where you see positive slopes and then slopes of zero, definitely the first thing you should do is look at the axes. What I have is a temperature on my y-axis and Q, which is my heat, in my x-axis. So as my heat increases, my temperature could increase or might not increase. This is an example of a heating curve. So there are different stages at heating a material in different phases. So we're just looking at different parts of the heating curve, and then we want to figure out what is the heat associated with this transition from point F to point A. So on a heating curve, you can go in one of two directions. You can go from the left to the right, which is going to be adding heat, or you can go from the right to the left, which is removing heat. So you're cooling things down. Anytime that you have a slope of zero, so slope equaling zero, this should tell you that you have a phase change. And the reason that this should tell you that is because if you look at your y-axis, if you have a slope of zero, there is no temperature being changed at all. So at this point, for such as B and C or D and E, you're putting a bunch of heat in, but there's no temperature change that's resulting. So when we have parts such as B, C, and D, E, well, we have our phase changes. And if we look closely, we'll understand what phase change is occurring where. Especially if you notice that the point A is at the lowest temperature, and as you increase the heat, you're going to have a horizontal bar, then a really long, really high temperature jump, and then another horizontal bar. So there are three different phases: solids, liquids, and gases. So I can assume that the lowest temperature will be a solid, and as you increase the temperature, you'll have a phase change to liquid. So anytime that you have these positive slopes, so a slope that is greater than zero, all you're really doing is you're heating the phase. So when I talk about A and B, what I'm doing is I'm going to put this in quotations, I am heating a solid, because that is at my lowest temperature. And if I go from a C to D, what I'll be doing is I'll be heating my liquid. And then from E to F, I'll be heating our gas. Now, I'm putting heating in quotation marks because we're using heat to describe energy. Also, there's this process of cooling, which goes from the opposite direction. So I'm using basically more of a vernacular term for heating, just a process in which I'm putting something in or taking something out, and that something happens to be energy. So I can identify all of these parts. I still don't know what BC or DE is. But now that I know what AB and CD are, so I know I'm heating a solid and heating a liquid, this means that BC is going to be my fusion phase change. And this is where I'm either going to have melting occur or freezing occur. The reason I label that as fusion is because if you look at enthalpy values associated with heating curves, we utilize the enthalpy of fusion for melting or for freezing. And now we can also identify what's occurring at DE, that's our vaporization. Because I'm either converting a liquid to a gas in vapor form, or I'm going to go from gas to liquid, which is condensation. So I know what my phase changes are, I know what my heating curves are as far as like what's being heated, what's causing a phase change, and so forth. The question is now, what is the heat associated with the transition from F to A? Well, it's just going to be a sum of all of those individual heating steps. So it's the sum, so Q total, is going to be the sum of every heating step. So I'm going to have a heat associated with A to B, a heat associated with C to D, a heat associated with E and F, and then I'm going to have a heat associated with B, C, and a heat associated with D and E. There's a reason why I'm separating them out. There are two different formulas that we can use for heat. Heat is going to equal either our mass times the specific heat times the change in temperature. Now, this is associated with either heating or cooling something down. The other thing that you can have, the other formula that you'll use, is the number of moles times the enthalpy of the phase change itself. So since I have in this heating curve, I have 3 heating of my phases and 2 phase changes, I'm going to group them together. So I'm going to have M, C solid, change in temperature of the solid, plus M, C of the liquid times the change in temperature of the liquid, plus mc of the gas times the change in temperature of the gas, plus the number of moles times my phase change of fusion, my enthalpy of fusion, plus the number of moles times the enthalpy of vaporization. However, the one thing that I want to point out, though, is yes, I can take the sum of all of these and my masses will not change, nor will my number of moles, because I'm not undergoing any type of removal process. All I'm really doing is just changing the physical state. The key to this is I'm transitioning from F to A. So this Q total has to be less than 0, because you're removing heat from the system in order to cool it down. So you can do all of these steps, but you must remember what direction you're going in. If you're going from left to right, you're putting heat in to cause the melting to occur and then causing the gas to form. But if you're starting with a gas, you need to remove heat in order for it to condense down and then solidify as a solid.